This is a generic digital communication system employing pulse code modulation. We start with signal X of T, which is the message signal. It's a continuous analog signal. It is applied to an anti-aliasing filter, which is essentially a low-pass filter, to give the message signal a sharp band limit in bandwidth. So the result of the filtering is a band-limited analog signal. This analog signal is applied to an electronic sampler. This is an electronic circuit controlled by a clock that will sample the value of the analog signal periodically at regular periods. The result of the sampler is a flat top pulse amplitude modulated signal. This sampled signal is then applied to a quantizer. The quantizer takes the sampled signal, rounds the value of the sampled signal off to its nearest standard value, and then expresses that, that becomes the quantized pulse amplitude modulated signal. Then after the sampled signal is rounded off to its nearest standard value, that value is then encoded as a binary number using a certain number of bits. The quantizer has a certain number of levels. The number of levels in the quantizer is determined by the number of bits used in the binary word. N is the number of bits. The number of levels is 2 to the power of n. So 4 bits would be 16 levels, 5 bits, 32 levels, etc. Although in practice, it's usually 10 or 14 bits. Okay, so this now is a binary signal, a string of ones and zeros that is applied to an encoder. So the string of ones and zeros are represented in a particular fashion. This now is the pulse code modulated signal, or the pulse code signal anyway, which can then be transmitted. We'll talk about how it would be used to modulate a carrier later on, but this digital signal will be transmitted, and in the course of transmission there will be noise perhaps added to the digital signal, or the digital signal will become distorted in some fashion. But the good news about a digital signal is that in many cases, and for a pretty wide variety of problems in a signal, the original signal can be recovered through a regenerative repeater. So the degraded digital signal is then spruced up, and the original digital signal reproduced accurately with essentially no errors in a good system. And then this digital signal is applied to a decoder, which takes the string of ones and zeros and turns it back into a quantized pulse amplitude modulated signal, which will be essentially a stair-step signal representing the digitized signal. That is passed through a low-pass filter, and the result is a close replica of the original signal. The transmitter part of the system is an analog to digital conversion process, and then at the receiver we have a digital to analog conversion process. The resulting signal is a close replica of the original signal X of T, and that's indicated with this little hat above the X. It will never be an exact replica of the original signal X of t, because in the quantization process we have rounded values off to their nearest standard values. And once you've rounded the values off to a standard value, you've lost the additional information. Part of what we're going to investigate are the limits on the noise that is induced into the signal because of this quantization. Now, this has turned out to be a pretty popular form of signal transmission and information transmission, so much so that you probably in your lifetime have not heard much analog sound, music specifically. Perhaps, well, even in live performances, sometimes they sneak in some digital processing. Live performances perhaps could be all analog, but if you're listening to some kind of recorded signal or something transmitted over a distance, it's probably been a digital communication system. Now, the advantages, it tends to be noise resistant. The digitized signal, which is represented by either one of two voltage levels, 0 and 5 volts, or 0 and some other voltage, or two voltage levels nonetheless, that can endure a significant amount of noise in some cases, and still we can recover the ones and the zeros. So that's noise resistance. There are ways to encode the information so that errors can be corrected. That is an advantage as well. And as we saw with our exercise in the last presentation, signals can then be multiplexed using time division multiplexing, and this allows even more information to be transmitted on common channels. As we investigated in the previous presentation, we looked at the process of sampling, and the key feature in the process of sampling is the sampling rate. That is the number of samples per second that you take of the analog signal. We through the Nyquist theorem, we determined that the sampling rate has to be greater than or equal to twice the bandwidth of the message signal. So the message signal has a bandwidth B. In setting up the sampler, we have to have a sampling rate that is greater than or equal to twice the bandwidth of the message signal. So that's twice the highest frequency content in the message signal. We can use the letters SR for sampling rate. That's the same thing as F with the subscript S. This would be the sampling frequency. That's exactly the same thing, just different words. It's got to be greater than or equal to twice the bandwidth of the message signal, and this is required by the mathematical theory in order to reconstruct the sampled signal from the samples. If you don't have a sampling rate that's high enough, you just simply mathematically cannot reconstruct the original signal accurately. So the sampling rate is one of the features of the sampler. The quantizer uses a certain number of bits to represent each sample. That is useful in determining the bit rate of the encoded data. See, the encoded data is a binary signal at a certain bit rate. So the binary signal is a serial binary signal that is that possesses a certain number of bits per second, and the bit rate. So the bit rate is simply BR. The bit rate is equal to the sampling rate times the number of bits per sample. See the bit rate. The bit rate in bits per second is equal to the sampling rate, that's in samples per second, and then we multiply that by n, which is the number of bits per sample. So samples cancel, and we get the bit rate is in bits per second. After the sampler, the sampled signal goes into a quantizer. The quantizer rounds the sampled value off to its nearest standard value. Here is a graphic demonstration of the quantizer. The thin line, continuous line, is the message signal x of t, and it is being sampled periodically at discrete points in time, and those discrete points are indicated on the time axis. This is time, and the sample is the signal is sampled periodically with sampling period t sub s. So this is the sampling period. The sampling period is the reciprocal of the sampling frequency. So the sampling frequency is 1 over t sub s, which is the same thing as saying the sampling rate is equal to 1 over t sub s. At each sampling point, the value of the message signal is rounded off to its nearest standard value. We establish the values, the standard values, by defining the input range of the quantizer. This would be a voltage, let's say, and this is 0 volts in the middle. The quantizer has a maximum input voltage of plus MP, so this is the peak input input value is equal to plus MP, and the quantizer ranges from minus MP up to plus MP, so its overall range is equal to 2 times MP. This input range is divided into L equal levels. Each level has an equal height. So the spacing between the levels is the overall input range 2 times MP divided by the number of levels L. Now the number of levels is related to the number of bits we are using to represent the signal. The number of levels L is equal to 2 to the power of n. L has to be a power of 2, and we are using n bits per sample. Okay, so once you've established the number of bits, then 2 to the power of n will give you the number of levels, and 2 MP divided by L will give the spacing between the levels. Okay, so again, at each sampling time, the measured value of the signal is rounded off to the nearest standard value, which is lies halfway in the middle between the lines, halfway between in each level. So in some cases, it's rounded to a higher value. In other cases, it's rounded to a lower value. Every now and then, the sampled value and the average and the standard value lie pretty close together, but that just happens by coincidence occasionally. In general, they are some distance apart sometimes. Okay. Now it is this rounding from the measured value to the standard value that induces noise into the sampled quantized signal. And once we've put this noise into the quantized signal, we cannot get the noise out. It is there forever. Here's another graphic demonstration of the quantizer. In this case, the input voltage to the quantizer lies on the horizontal axis, and it could go from minus some voltage to plus some voltage. I really haven't indicated the peak range in this case. And the output voltage is mapped onto the vertical axis. And in this case, we are given 8 levels. So L is equal to 8 levels. Since L is equal to the power of n, that makes n equal to 3 bits per sample. And we've indicated the 3-bit words that will be used to designate each of the voltage levels or signal levels. So, for example, if the input signal lies between 0 and 2 volts, that is rounded off to the nearest standard value of 1, and that is identified with the binary word 100, the 3-bit binary word 100. If the voltage lies between 4 and 6, it is rounded off to the standard value of 5, and that is the binary value 110. If the voltage lies between -6 and -4, that is rounded off to the standard value of -5, and that is given the 3-bit code 001. Let me remind you of what we discussed with ideal sampling. We've got, I'm going to use M of t as the message signal going into an ideal sampler. That samples the message signal M of t periodically. Then the signal that comes out of the sampler is M with a subscript S of t. This is the sampled signal, and as we discussed, this sampled signal is equal to, it's a summation over index number k of a string of shifted delta functions. Each of the delta function has a weight factor given by the message signal M, evaluated at times k times t sub s, and then that is the weight factor for a delta function t minus k times t sub s. So this sampled signal is a sum of weighted delta functions. The method that we established to reconstruct the message signal is to take the sampled signal into a low-pass filter, and if this is an ideal low-pass filter, let's give it a transfer function h equal to rect of let's see, we're going to have f divided by 2 times b. Okay, that would give us, this would give us the transfer function, which would make the impulse response, let me be more explicit, this is h of f, transfer function as a function of frequency, that which is going, so the impulse response is the inverse Fourier transform, so that's going to be 2b times the sinc of 2b times t, which is going to be 2b times the sinc of t divided by 1 over 2b. And the signal that comes out of the low-pass filter then is going to be the signal that goes into the low-pass filter. That's going to be m sub s of t. And then that's going to be convolved with this impulse response, and this reconstructs the message signal m of t. And when we carry out this convolution, we get m of t is equal to the summation over k. See, we're convolving a train of delta functions with the sinc function. So what we get from this convolution is a summation of sinc functions, and that's going to be m. Let's see. Each sinc function will have a weight factor given by the sampled message signal. And now this is going to be times sinc. You got to hang on. I'm running out of blue forced ink to change to black ink in the middle of an equation. Okay. So it is a summation of weighted sinc functions, and carrying out the convolution gives us sinc of t minus k times t sub s divided by t sub s. So our reconstructed message signal is the sum of weighted sinc functions. Each one of these sinc functions is, here I'll show it this way, for some value of k, is shifted to the location of k times t sub s, and it's got a weight factor that gives it the peak value here of m times k t sub s, and then it's a sinc function. It is a sinc function that has 0 crossings at 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. It has this would be k plus 1 times t sub s is its first 0 crossing after from its center, and this would be k minus 1 times t sub s, and then the sinc function would look something like this. I'll just draw a bit of it. Then the next shifted sinc function is lined up with the 0 crossing from this sinc function, and I'll go to another diagram to show you what that looks like. This is an illustration of the use of shifted sinc functions to reconstruct our original message signal. We have a summation over index number k of sinc functions. Each of these sinc functions is shifted to a particular location that would be for each value of k, the sinc function is shifted to k times t sub s, and then the width of the or the zero crossings for the sinc functions is given by the value of t sub s. So that gives us this series of shifted and scaled sinc functions. Each of the sinc functions is got a scale factor given by the value of the message signal at time k times t sub s. When we add these shifted and scaled sinc functions together, we reconstruct the original message signal. So the sampling period in this case has been, the sampling frequency has been set to equal to 2 times b. B is the bandwidth of the original message signal. So this is the illustration for sampling, ideal sampling at the Nyquist rate. So with ideal sampling, the message signal can be reconstructed by the summation of shifted sinc functions. And if we consider sampling the signal at the Nyquist rate, which would make the sampling frequency equal to twice the bandwidth of the message signal, so the reciprocal, so the sampling period is the reciprocal of the sampling frequency, so that's going to be 1 over 2b. That will give us the sampling period. So substituting that back into this equation, we can write the equation for the reconstructed signal and with ideal sampling. This is I can't write ideal. Ideal sampling. So this gives us m of t. With quantized sampling, the signal is reconstructed using the quantized samples. These are not the ideal samples. These have been rounded off to the nearest standard value, and that will result in an approximate signal. That's m with a hat above it. So there is an error between the ideal reconstructed signal and the approximate reconstructed signal. That error signal is simply the difference between the two. So if we take the approximate signal and we subtract the ideal reconstructed signal, then we will get then the error. That will make the approximate signal equal to the ideal signal plus the error. And if we substitute for m hat this summation, and we substitute for m of t this summation, and we factor out we factor out the terms correctly, we will get the error signal is a summation over k of these shifted and scaled sinc functions. But now the scale factor is the difference between the quantized weight factor minus the ideal weight factor. That's it. So this is, in fact, the error. So the error signal is a summation over index number k of the error for each of the sampling, each of the signal samples. This q is the approximate sampled value minus the ideal sampled value. That gives us the error for each sample, and that multiplies our shifted. Now what we want to do is we want to find the power in the reconstructed signal. So we would take this reconstructed signal for m hat, we square it and take the time average. When we square this summation, we're multiplying two sums, infinite sums across each other, and then taking the time average, and they would That would normally be an infinite task, of course, but it turns out that the sinc function is orthogonal, so that all of the cross sinc function terms, they time average to 0. It is only the when you multiply a shifted sinc function with itself and find the area, find the time average, that you get a value. And so that what that will lead us to now is the power in the reconstructed signal is equal to the error signal squared and time averaged. And the error signal is the ideal signal plus the error signal, and then we square that and take the time average. When we square this this term in the square brackets, we get m squared plus the cross term. Actually, there should be a 2 in there. This should be 2 times m sub t times q of t plus a q squared of t. And then we're going to take the time average, and we can then time average each term individually. Now when you multiply the message signal by the error signal has an average value of 0. So multiplying this average signal with an average value of 0 times the message signal and taking the time average makes that term go to 0. So we have, that's because the time average of the error signal is 0. So this cross term goes away, and what we are left with is the power in the reconstructed signal is equal to the power in the message signal plus the power in the error signal. Okay, so we can separate the power in the message signal from the power in the error signal, and the total power in the reconstructed signal is the sum of these two terms. The total power in our reconstructed signal, this is the total power, is equal to the signal power. This is the signal power plus the error power, that's the noise power, plus the noise power. Signal and noise are not correlated to each other. So total power is equal to the signal power plus the noise power. The quality of such a signal can be measured using the signal to noise. This is a power ratio. So the signal to noise ratio is equal to the signal power divided by the noise power. And the higher this number, the higher the quality of the signal. So for our reconstructed signal, the higher this signal to noise ratio, the higher the quality of the reconstructed signal. And it is a power ratio, so we're taking the ratio of the signal power, we're taking the signal power and dividing by the noise power. This is a signal to noise ratio. This signal to noise ratio in this form is not a very useful number to look at. It can be quite large, and it's hard to get a handle on it. If we want the signal to noise ratio in bells, we take the log base 10 of the signal power divided by the noise power. So this is the signal power, and we divide by the noise power. This will give the signal to noise ratio in units called bells. Now this turns out not to be as useful as the more traditional way of looking at this measurement in units of decibels. So the signal to noise ratio in units of decibels is equal to 10 times the log base 10 of the signal power divided by the noise power. So to find the signal to noise ratio for any signal in decibels, you take the signal power, divide by the noise power, then take the log base 10 of that, and then multiply by 10, and that gives the signal to noise ratio in the units of decibels, which is the traditional way of measuring a signal to noise ratio. Okay, to find the signal to noise ratio for our quantized signal, we need to get a handle on the noise power. And the noise power comes about due to the error between the measured value of our signal, sampled signal, and the rounded off quantized value. So this is our continuous message signal, let's say x of t, and we have a sampling time indicated at this instant. Now at this instant the measured value is shown with this dot, and the nearest standard value is shown with the dot that lies halfway in between the levels for the quantizer. And the error is going to be m hat minus m. That will give us the error. And we set that equal to the value q. So the error q is equal to m hat. That's the standardized value for the measured value minus the actual measured value m. Now these the levels are such that there is a delta V between the two levels, which is equal to 2 times MP divided by L. When we set up the digitizer back ages ago, it seems, remember that we had a digitizer that had a total input range from minus MP to plus MP, so that's a total range of 2 MP, and you divide that by the number of levels L, and you get the spacing between the levels. Well, that's what we have here as the spacing between the levels, 2 MP divided by L. We're calling that delta V. The standard value lies right in the middle at delta V over 2 from each of the edges, and the sampled value lies somewhere in this range. Now, we don't have any reason to believe that it would be at one place any more likely than any other place. So the probability for the measured value we can show on a probability density function. This is a tool you should have picked up in your probability and statistics course. This is the probability density function for the value of the error Q. It ranges from, the value for Q can range from minus delta V over 2, if it's here at the bottom, to plus delta V over 2, if the measured value is here at the top. So its overall possibilities have a width of delta V, and since it's a probability density function, we have to keep it's a uniform probability density function, so we have to keep the area of this rectangle equal to 1. So that makes the height of the rectangle equal to 1 over delta V. So delta V times delta V is equal to 1. That is a proper probability density function. Now we can find the average noise power. We're not going to find, we're going to find the average noise power by finding the statistical average of Q squared using this probability density function. So this again would be a tool you would pick up in the statistics and probability course. Anytime we want to know the average value or the expected value of something, Q squared in this case, we take Q squared and then we multiply by the probability density function, and then we integrate over all values of Q. So when we do this and we set up this integral, the way that will be set up will look like this. We will have the time average of the error signal. This will give us the noise power. It's going to be equal to the integral, and we only have to integrate from minus delta V over 2 to plus delta V over 2 because we have a 0 everywhere else. So that's minus delta V divided by 2 to plus delta V divided by 2. And now we take Q squared, and we multiply by the probability density function in between this range. That's 1 over delta V, and we are integrating with respect to Q. So let's carry out this integration, and perhaps this is calculus so easy that even I can do it. So the noise power found from the statistical average is going to be 1/3 Q to the third power, and we evaluate, see, I've got a 1 over delta V times 1/3 Q to the third power, and we're evaluating from a minus delta V over 2 to plus delta V over 2. So this is going to be 1 over 3 times delta V, and we put in the upper limit of integration. Delta V over 2 to the third power is delta V to the third power divided by 2 to the third power is 8, and then minus delta V to the third power. See, we're subtracting at the lower limit of integration. You put in minus delta V to the third power. That's going to make that a plus, and we have delta V to the third power again divided by 8. And then so we add these two together, and we get 1 over 3 times delta V, and we add these two together and we get 2/8, so that's going to be delta V to the third power divided by 4, which is going to be equal to 1 over 12 times delta V squared. And this is the noise power in the error signal. And remember that delta V is equal to 2 MP over L. So this is going to be equal to 1/12, and delta V is twice the peak range of the digitizer divided by the number of levels. So delta V is 2 MP over L, and then that's going to be squared. So this is going to be 2 squared gives us 4, and we have MP squared divided by, we have a 12, and then in the denominator an L squared. This gives us the average power in the noise, in the error signal. So the noise, that's time averaged, so the noise signal is going to be equal to MP squared divided by 3L squared. Okay, this is the noise power In the numerator of this fraction, we have MP squared. So the larger the input range of the digitizer, the larger the noise power. And we have L, the number of levels, in the denominator. So the more levels we have, the smaller the noise power. So in order to minimize the noise power, we want to make the overall range as small as we can, and we want to make the number of levels as large as we can within whatever other limits we have to constrain us. Okay, now we're ready to find the signal to noise ratio for our quantized signal. So this is the quantization noise, or the quantization signal to noise power. So we take the signal power of our message, which is simply the message squared time averaged. So this is the top of the fraction is the signal power. In the top of the ratio, in the bottom of the fraction, we have the noise power for the quantization noise, and we work that out to be MP squared divided by 3L squared. That goes in the bottom of the fraction. We do just a little bit of 8th grade algebra, and we can write that the signal to noise ratio for uniform quantization. Now this I haven't emphasized this enough, but remember when we set the quantizer up ages ago, we set it up with uniform spacing for all of the levels. This is uniform quantization. And we've worked out now the signal to noise ratio for a quantizer with uniform quantization. That signal to noise ratio is 3 times L squared times the message power. This again is the message signal power. It's not the message signal squared, it's the message signal squared and then time averaged. So that's the message signal power. That will be determined by the character of our message signal when we work out examples. That is divided by the peak range of the peak range of the quantizer, and then we square that number, and that's in the denominator of the fraction. And then L is the number of levels that we use in our uniform quantizer. This signal to noise ratio, if we want a good quality result, we want this number to be large. In order to make the signal to noise ratio large, we can increase the number of levels, or we can minimize the peak range of the quantizer. And those are the things that we can control, presuming we're given a certain message. If we want for a given message to maximize the signal to noise ratio, we increase the number of levels to whatever limits may be placed on us, and we fit the message signal more closely to the peak range of the quantizer. Okay, so this is a result we want to remember. We will use this equation to analyze various quantizers. Let me work a simple numerical example while I'm thinking of it. Let's consider a message signal M of t into an 8-bit quantizer. I'm just picking 8 bits just just as an example, not that it's realistic for any practical purpose, but just as an example. And what will result is a quantized signal. We've got n, the number of bits per sample, equal to 8. So that makes the number of levels 2 to the power of 8. And 2 to the 8th power is, let's see, 2, 4, 8, 16, 32, 64, 128, 256. That's 256 levels. Then let's say, for example, now the message signal is a sinusoid, amplitude 1 times cosine 2 pi f. This is f of our message times t. So our message signal is a simple sinusoid. This is the message signal. And our quantizer, let's give it a peak range, MP, of 5 volts. So our message signal is a cosine that has an amplitude of 1. And our quantizer has a peak range of 5 volts. So its peak range is between -5 and +5. And it's got a frequency of f sub m. So the Nyquist sampling rate is going to be equal to 2 times whatever the frequency of this signal is. This would be the Nyquist rate. The Nyquist sampling rate, twice the highest frequency component in the message signal. Now let's see what happens. Let's find the signal to noise ratio for this quantized signal. The signal to noise ratio is going to be equal to the 3 times the number of levels squared times the message power, message squared and time averaged, divided by the peak voltage, peak range of the digitizer squared. Now the message signal, the average power in the message signal, m squared time average, that's the average power in this cosine. Well, that is always 1/2 the amplitude squared, so that's going to be 0.5 watts is the average power in this cosine. MP is equal to 5. See, it's not 10, it's 5 as the value for MP. And the number of levels is equal to 256. So the signal to noise ratio is simply going to be 3 times 256 squared times 0.5. That's the average message. That's the message signal power divided by 5 squared. And by my calculator, where is my calculator? There it is. Here it is, just to show that I have a calculator. 3 times 256 squared times 1/2, and multiply those, and then I divide by 25, and I get as the power ratio 3932.116. That is the signal to noise ratio, power ratio. This is the power ratio. Now, if we want to know the value in decibels, the signal to noise ratio in decibels is going to be 10 times the log base 10 of this signal to noise ratio, so that's going to be 3932.16. And by my calculator, let's see, log base 10 right there, and then multiply by 10, that is a signal to noise ratio of 35.9 decibels. Okay. Now, this signal to noise ratio is determined first of all by the signal power, which was given to us when we knew the amplitude of the cosine, and it is completely dependent otherwise upon the peak range of the digitizer and the number of levels. If we wanted to improve this signal to noise ratio, we could increase the number of levels, which would mean increasing from 8 bits to 9 or 10 or 14 or whatever. That would increase the signal to noise ratio. Or we could fit the range, the peak range of the digitizer more closely to the signal. If we had a smaller peak range on the digitizer, that would also, and the same number of levels, that would also increase the signal to noise ratio. Another method to improve the signal to noise ratio of a quantized signal is called non-uniform quantization or compression. For many signals, like voice signals or music signals perhaps, most of the time the signal has a relatively low amplitude, or a relatively low level. It goes plus and minus, but it's relatively close to the zero line. And then only on occasion does it get larger in size. Compression takes advantage of this by spacing the levels more closely together in a non-uniform fashion. There's not equal spacing between the lines in this quantizer. When we're close to zero, they're spaced more closely together. And then for larger sizes when the signal is in a larger size, the level lines are more widely spaced. This is a non-uniform quantization, and it is often called compression. Not to be confused with data compression, which is something else altogether. So we still have our message signal x of t. And we still have L levels. I don't see what this is. It's non-uniform anymore, so I think I should remove this from the diagram because it doesn't tell us the spacing between the levels. We still are sampling periodically with a certain sampling period, and presuming we're meeting the Nyquist criteria. The compression technique commonly used in this country is called a mu-law compressor. We have our message signal M that goes into a circuit that we'll model it this way anyway. That we're modeling it as a circuit that compresses the input signal, producing a compressed signal Y, and then that we'll apply to a uniform quantizer, and then the message at the receiving end will be decoded. And then there is a circuit called an expander that reverses the effect of the compressor, and we retrieve our our approximate signal from the sampled values. So this is an equation for a mu law compressor. The output of the compressor Y is given by this equation, 1 over the natural log of 1 plus mu times the natural log of 1 plus mu times m divided by mp. This is good for the ratio of m to mp between 0 and 1. This equation gives the compressed value for Y. And it depends upon the compression factor mu. And depending upon the value of mu, you can go from no compression at all. See, this is the ratio of the message value to the peak of the digitizer. That would go from 0 to 1. And here is the value of Y, which also goes, the compressed value, which also goes from 0 to 1. With no compression at all, this is a linear relationship. But with different values of mu, different degrees of compression, you get these other curves that illustrate the input and the output. So if you take a relatively small value of input, let's say that the peak range is equal to 1, and our message value samples to be 0.1. So with no compression at all, that maps to a value of 0.1. With a compression factor of 10, that maps to a value of 0.3. And with a compression factor of 1,000, a 0.1 input would map to a compressed value of about 0.7. So we are compressing this. We are using for small input values, we are spreading that out across a larger range. In effect, putting the levels closer together for small values. Okay, so if you take the compressor and the expander combination together, that's often called a compander. I don't know why. I also don't know why I have an O here and an E here. That's not consistent. I'll have to figure out which I want to use. Now we need an equation for the signal to noise ratio when using a compressor, employing non-uniform quantization and using a compressor. And your textbook takes the easy way out and refers to a derivation in the appendix, I believe it is, which is lengthy and will likely not give us a lot of insight. But we will use the result that is expressed in our textbook for compression with a mu law compressor. And this is the equation as listed in our textbook. We will accept it without bothering to derive it. The signal to noise ratio with a mu law compressor is equal to 3 times L squared, which is convenient because we also have that term. See, that's the same 3 times L squared that we have in the expression for the uniform quantizer. But in the denominator, we have the natural log of 1 plus mu. Mu is the compression factor, which could be, see, we saw in this chart, we had values of mu at 10 and 100 and an extreme at 1,000. So mu would have a number somewhere around 100 or so, depending upon our system. So we take the natural log of 1 plus mu and then square that result, and that's in the denominator of this fraction. And this will give us an equation for the signal to noise ratio. Your textbook also has this chart that shows, compares uniform quantization with mu law compression. Without compression, that would be uniform quantization. That's represented by this mu equals 0 line. So this is uniform quantization. along the horizontal axis is the relative signal power. This is the power of our message signal in decibels. So it starts at 0 decibels and it increases. And along the vertical axis is the signal to noise ratio in decibels. So you can see for a particular value of message signal power, then with uniform quantization we get a certain, let me pick just for an example, let's pick this value for the message signal power, 30 decibels, and with uniform quantization that would result in a signal to noise ratio of let's call it 25 decibels, just to give it a number. If we used a mu law compressor with a mu value of 255, that same input signal would give a signal to noise ratio of let's call that 37 decibels. So with uniform quantization we get 25 decibels. With the mu law compander we get 39, let's call it 37 decibels. I'm just eyeballing it. So with this smaller signal power, it is an advantage to use the compressor because we get a better signal to noise ratio. However, if we have more signal power, which is to say, if we look back at our graphic illustration here, if our signal spends more of its time at these higher sizes, higher magnitudes, where we are getting less accurate quantized values, then there becomes a point where the compressor is not helpful for us. Let's say we consider a more powerful message signal, 50 decibels in this case. If we look the compressed with the mu law compressor, we get about 40 decibels signal to noise. But if we simply used uniform quantization, we would get something like 45 decibels signal to noise ratio. So with the high-powered signals, sometimes it's better to use uniform quantization, and with low-power signals, it would be better to use the quantizer. I'm sorry, the compressor, the compander. And so obviously there's a crossover point, and that's kind of interesting. Okay, now I would like to do a comparison. Let's compare uniform quantization. We'll take a message signal into a uniform quantizer. Let's say the number of levels is equal to 256, and the peak range, let's say, is equal to 1. The signal that comes out is m hat of t. We'll let our message signal be a sinusoid, amplitude A times the cosine 2 pi some frequency times t. We know that the power in the message signal, square the signal, take the time average, that gives the power. Power in a cosine is always 1/2 the amplitude squared. The signal to noise ratio is going to be equal to 3 times L squared times the message signal power divided by the peak range of the quantizer squared. And in our example, that's going to be 3 times 256 squared. The average power is going to be 1/2 a squared, and then divide by MP squared is 1 squared. So the signal to noise ratio is going to be, see, this will be a constant, 3 times 256 squared divided by 2 divided by 1 squared. This, by my calculator, turns out to be 98,304 times the amplitude squared. Okay, this is the power ratio. The signal to noise ratio in decibels is going to be equal to 10 times the log base 10 of this value, 98,304 a squared. Now we can make a chart that we have the amplitude in the first column. Make it range 0.1 smallest value. Then it can range upward to 0.7, 0.8, 0.9, 1.0. We'll have it range from 0.1 all the way up to 1.0, which matches the peak range, the peak input range of the digitizer. And for each of these amplitudes, we can determine the signal to noise ratio in decibels. I'm going to stop the recording and go do that, so you won't have to be bored watching me punch numbers into my calculator. So I've done the calculations for a uniform quantizer, 256 levels, a peak range of 1, so it goes from -1 volt to +1 volt. A message signal that is just a cosine with a certain amplitude. We worked out that the signal to noise ratio is given by this equation related to the amplitude squared. So I made a chart of the amplitude for the message signal, small to large. 1.0 is the largest we can use with this particular quantizer. And here is the corresponding signal to noise ratio in decibels. Now I want to do the same similar calculation for a mu law quantizer. So this is for a mu law quantizer. This is non-uniform quantization. We take the same message signal into the mu law quantizer. It's got 256 levels again, and it's got the same peak range, but we have a compression factor. Let's take a compression factor of 100, just so we'll have something to calculate with. Now the signal to noise ratio for the mu law quantizer is equal to 3 times L squared divided by, we have the natural log of mu plus 1, and then we square that value. So for our example, that's going to be 3 times 256 squared divided by the natural log of 101, and we square that value, and we get a signal to noise ratio for the mu law quantizer. By my calculation, 3 times 256 squared, 101, we take the natural log, and then I square that, and I divide, and I get 9,230 for the power ratio. And if we want to, tipped it over, the signal to noise ratio for the mu law compressor or quantizer in decibels is going to be 10 times the log base 10 of 9,230, which is log base 10 times that, 39.65 decibels. Okay, and it is 39.65 decibels regardless of the amplitude of the message signal. We still have the same message signal. And regardless of its amplitude, as long as the amplitude, of course, is no greater than 1, we'll count the signal to noise ratio to be 36.7 decibels. The proper tool to compare these two quantizers is Excel. I can make I made a spreadsheet with the first column is the message amplitude, ranges from 0.1 to 1. The second column calculates the signal to noise power ratio according to the formula that is in the notes. The third column is that power signal to noise ratio in decibels, ranging from 29.9 to 49. And then I have a column for the signal to noise power ratio for a mu law quantizer with the same number of levels and a mu factor of 100. That's 9231. And in decibels, that works out to be 39.7. So that's plotted in this chart. We have the message signal amplitude along the horizontal axis and the signal to noise ratio along the vertical axis. And the blue line is the uniform quantizer. It starts at a value of about 30 decibels and at a small amplitude, and then as the amplitude increases for the message signal, the signal to noise ratio also increases. With the mu law quantizer, we have the constant value of just under 40 decibels. So for small amplitudes, less than about 0.3 volts, the mu law, the compressor quantizer would perform better. And for signals with higher amplitudes above 0.3, the uniform quantizer performs better. Allow me to do one more example. Let's consider uniform quantization with a message signal M of t into a uniform quantizer. The signal that comes out is the quantized signal M hat of t. I don't know how many levels I want to use. Let's use a peak range of 5 volts again. But the criteria I want to hit is a signal to noise ratio in decibels equal to 35 decibels. And one more thing, let's take the message signal power, m squared time averaged. Let's say that's 4.5 watts, just to give it a number to work with. The question is, how many levels for this quantizer, and then how many bits per sample for this quantizer? So our criteria for the signal to noise ratio is 35 decibels. That means 10 times the log base 10 of the signal to noise power ratio is equal to 35 decibels. That means log base 10 of the signal to noise ratio is 3.5, which if you take both sides to the power of 10, that makes the signal to noise power ratio equal to 10 to the power of 3.5, which by my calculator is 3,162.3. So we can now use the equation that 3L squared times the message signal power divided by the peak range of the digitizer squared is equal to the signal to noise ratio. We can set that equal to the signal to noise power ratio, and we solve for L. That's going to make MP squared times the signal to noise power ratio divided by 3 times the message signal power, and then we take the square root. That will give us the number of levels. So if we plug in our numbers, the peak range of the quantizer is 5, so 5 squared. Signal to noise ratio, power ratio is 3,162.3. Then we divide by 3 times the signal power, which is 4.5 watts. And then we take the square root. And if you'll be patient as I punch away, 5 squared is 25 times 3,162.3. And we divide by 3 times 4.5, and that, then take the square root, and I get 76.5 levels. That's the number of levels required to achieve a 35 decibel signal to noise ratio. However, our number of levels has to be a power of 2. 76.5 is not a power of 2. I have to use the next larger power of 2, so I have to use L equal to 128, which corresponds to the number of bits, 7 bits per sample, and 128 levels. See, 2, 4, 8, 16, 32, 64, 128. That's right, 7 bits per sample. Now, if I use 128 levels, I'm going to have something better than a 35 decibel signal to noise ratio. So let me determine exactly what that will be. The signal to noise ratio is going to be 3 times 128 levels squared times the power, which is 4.5, divided by 5 squared. That, by my calculation, gives 3 times 128 squared times 4.5 divided by 25. That's 847.4, which convert that to decibels is take the log base 10 and multiply by 10. I get 39.5 decibels. Okay. So that meets the criteria. The 35 decibels here, that was a minimum, so I should have written this, the signal to noise ratio has got to be greater than or equal to 35 decibels. Okay.
Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
Delicious things to eat.
The popcorn can't be beat. The sparkling drinks are just dandy. The chocolate bars and the candy. So let's all go to the lobby to get ourselves a treat. Let's all go to the lobby to get ourselves a treat.